So we'll come back to this particular example, but let's talk generalities now. We've got a polar equation, or you might say a polar function, generating a polar curve graphed using polar coordinates like we just did. R equals f of theta. By the way, if your polar equation is not solved for r as a function of theta, if you can, you would try to do that before you make your graph. These kinds of things are easiest to graph, to find slopes of, to find arc lengths of, and to find areas. Not under the graphs, but swept out by the graphs. The area one is the trickiest, for certain situations at least. There's your polar equation generating a polar curve. How can we relate it to rectangular coordinates and use our knowledge about rectangular coordinates to do various things? The conversion equations, I wrote these down before, are x equals r cos theta and y equals r sine theta. What you can do is you can replace those r's with f of thetas. So x becomes f of theta times cosine of theta, and y becomes f of theta times sine of theta. Once you've done this, what you've really done is you have created parametric equations in the parameter theta instead of the parameter t. But the principle is still the same. You could still graph it using parametric mode on your calculator. In fact, as we do this general kinds of stuff, I will illustrate these ideas both with calculator and Mathematica. For our example, we're still going to consider r equals f of theta equals 2 plus 4 cos theta. If I want to graph that equation, that limaçon that I graph by hand in my calculator, there's two ways I can do it. In both ways, I need to change from function mode to something else. Either par for parametric or pole for polar. Let's start with pole for polar. This is something new. I'm in my mode screen. Mine looks like this. I choose pole for polar. When I go to y equals, just like happens with parametric mode, it looks different than usual. Now I go to y equals, I see r's. It's after functions of theta. My function of theta is 2 plus 4 cosine theta. How do I get a theta to show up? It is the same as the x button. And when you're in polar mode, it'll show up as a theta. So we're about to graph this on the calculator in polar mode. For the window, pick theta to go from 0 to 2 pi, about 6.28. The t-step it picked as a default is about 0.13. That's probably pi over something. If we're going to see the limaçon that I have graphed by hand in a good window for x and y, I picked x going from -2 to 7 and y going from -4 to 4 because it seemed reasonable, looking at the picture that I drew by hand. All right, now I'm about to hit graph. We should see that limaçon. Ready? 1, 2, 3, go. There it is. It's the scales on the x and y axes as a default are not the same in calculators. If you wanted to see it a bit more accurately when the scales are the same, we could do a zoom square under the zoom button, z square, enter that, it redraws it with the scales on the x and y axes being the same. And you might say that's how it truly looks. I could also graph this with parametric mode, this exact same curve. However, if I use parametric mode, go back to my mode screen, go to par instead of pole. If I use parametric mode, I don't plug in the function f of theta. Instead, I plug in these functions, although the calculator is going to use the letter t instead of theta. Doesn't matter. Yes, theta is an angle, it's not time. But we can still think of it as time if we want to. We could imagine time going by as the angle changes, effectively treating the angle as time or the time as the angle. Go to my y equals. F of theta, use parentheses here, is 2 plus 4 cos theta. It's going to be a t there. Continue using parentheses. All this gets multiplied by cos t. Cos theta written by hand. Go to the y. Use parentheses. 2 plus 4 cos still, because it's f of theta, involves cosine, not sine. This is cos t. Still the same f of theta, but now times sine theta, t in the calculator. Go to my window. T min max should be 0 to 2 pi. Actually, the x min max and y min and max here are the z square choices, I believe. I think I did this in the last class. You could do -2 to 7 like I did before if you want. Graph it. Ready? 1, 2, 3. We're going to see the exact same graph. There it is. Okay, so I made the same graph, first using polar mode, second using parametric mode. In Mathematica, I added something in here. I made what I'm calling a polar grid using show and polar plot. Polar plot 1, 2, 3, 4 is going to graph the equations, the polar equations r equals 1, r equals 2, r equals 3, and r equals 4. Very simple equations that, if you think about it carefully, are going to generate circles of varying radii centered at the origin. R equals a positive constant gives you circles. And actually, with our convention to go in the opposite direction when r is negative, even r equals a negative constant gives you circles. And then these are ordinary plots of lines at various angles. There's a polar grid, I'm calling it, that I'm going to use as the background of my polar plot. It's now stored in polar grid. If I type polar grid and re-enter it, it's the same plot that gets spit back. That entire plot is stored in this variable that I've called polar grid. I can show that plot, that polar grid, with another plot. Use polar plot to plot polar curves. Let me define f of theta up here as well. F of theta going to be 2 plus 4 cos theta. To make a theta, if you like, do escape th escape. Again, that's escape th escape to make a theta. I mean, you don't have to use a theta, but you know, it's fun to continue doing that. Theta is going from 0 to 2 pi. We see the finished product, not the tracing out. And it'd be nice to maybe make it stand out more. Plot style, arrow, say, oh, I don't know, how about purple? And make it thicker, like thickness 0.02. There we go. There's our limaçon. I did make the special angles here, by the way, for these lines be like 30, 45, 60, etc. There's our limaçon. If I try to make the exact same thing with parametric plot, that could be done with, yeah, parametric plot. But be careful, you'd be plotting f of theta times cos theta, comma, f of theta times sine theta. Theta goes from 0 to 2 pi. I can do the plot thickness thing here as well, I believe. Exact same graph.